Okay, so we looked at rate laws, relationship between rate of reaction and the concentration of a reactant. If we integrate the rate law, then we can look at the relationship between concentration of reactant and time. And this is very useful. It allows us to predict the concentration of reactants or products at some future time. Like in 10 minutes, what will the concentration be? And of course, the concentration is going to depend on the order of the reaction. So again, looking at a simple decomposition where A goes to products, we can look at a first order reaction. The rate would equal a constant times the concentration of A. We can express this as the rate is equal to negative delta A over delta T. And this is what we were doing at the very beginning of the chapter, defining the rate in terms of the concentration of reactants or products. So if we use calculus and integrate, we can get an integrated rate law, but I got ahead of myself. We can rearrange that and get a differential rate law. That's really not very useful. What's useful is the integrated rate law. And the good news is, we don't actually need to do the calculus. We can just believe them when they said, yeah, this is what you get if you integrate it. So what we do is we just use the equation. Okay? So integrating that law, we get the natural log of the concentration of A at some time t is equal to negative the rate constant times that time plus the natural log of the initial concentration. So this is the linear form. You can also express it this way. So if you remember the form of a line, y equals mx plus b. Y is graphed on the y-axis. Pointer got stuck. So we're graphing natural log of the concentration as a function of time. And then the slope of the line is equal to negative k. And the intercept is the natural log of the concentration of A at time 0. The slope is negative, but the rate constant is positive. And it just has to do with the integration, and so we should just not worry about it. So, any questions yet? We're going to do more graphing of things in 1B than we did in 1A. And so it's important to understand how this equation gives us a line. And that gives us a lot of, allows us to calculate things that would otherwise be impossible to calculate. Because how do you calculate the rate constant experimentally? Well, one way is to measure the concentration as it changes over time and graph it and get a nice line like this. So using that, let's look at this reaction, the decomposition of SO2Cl2. We monitored the concentration at a fixed temperature as a function of time during the decomposition, and the data was tabulated and it's presented there. And our goal here is to show that the reaction is first order and determine the rate constant. So we need to know the integrated rate law for a first order reaction. The natural log of the concentration of A at some time is equal to negative KT plus the natural log of A at time 0. I would encourage you to try to write the law from memory because it makes everything go faster, but then double check, and I'll give you these equations for the exam. So if this is the rate law for a first order reaction, then I want to graph the natural log of the concentration versus time. And so what I would need to do is, the time is fine, but I need to take all of these concentrations and find the natural log. Now this is not something that you're going to do calculating each of these with your calculator and then graphing them out on paper. That's very old school. Now we would do this on Excel, right? You get the data into Excel, you type the equation in once, you copy and paste, it does all the math for you. And then you drag the stuff into a graph. It's much easier that way. So, bingo, it's done. Graphing the natural log of the concentration of the reactant versus time. And we see that it's a straight line. So how do we show that this is a first order reaction? We graph it using the first order integrated rate law, and if we get a straight line, that confirms that it's first order. If this was a second order or zero order reaction, this data would not give a straight line. And we'd say, oh, well, it's not that, let's try one of the other ones. Yes?
Is first order always going to be a straight line?
First order will always give you a straight line when you graph natural log of reactant concentration versus time.
Okay.
Yep, always. So that's the showing that it's first order. And then we were asked to find the rate constant. Well, the rate constant is in the equation for the line. The computer that did the graph will also give us the best fit line and an equation for the line. So in the form y equals mx plus b, that corresponds to the natural log of concentration equal to negative kT plus the natural log of the initial concentration. So the slope is negative k. The slope is listed there as negative 0.000290, and that is equal to negative k. So then what's k? Positive 0.000290. Or with that many zeros, it might be good to put it in scientific notation. What are the units?
Since it's first order, it's per second.
Per second. Yeah, so we can't get the units by looking at this equation when you do natural logarithms and stuff. What happens to the units? I don't even know. But we know what they should be because it's first order, the rate equals the rate constant times the concentration. The rate has units of molarity per second. The concentration has units of molarity. And so for the rate constant, it must have a unit of 1/2. So this would be s to the minus 1. Any questions? There's some blank stares and some thinking frowns. Yes?
Will there be times where we have to find the slope, or will it give us the slope?
If you were doing this problem, say, for an experiment or for a homework problem, where you'd actually have to graph it, you would graph it in Excel, and Excel would tell you, you would tell Excel to tell you what the equation for the line is.
Okay.
You could graphically get it from a paper graph, but it's not going to be very precise. Yeah. Any other? Yes.
Can you just re-say the top part again?
Yeah, about the units.
Yeah.
So for first order reaction, the rate is equal to a constant times the concentration. And so we figure out the units on this constant. They are whatever is needed to make the other units work out. So we know that the unit on a rate is molarity per second because it's the change in concentration divided by the change in time. And the unit of concentration is molarity. And so then I ask myself, well, what does the unit here need to be so that the units will be the same on both sides? And that's how I come up with 1/2. Does that help?
Yeah, thank you.
Okay, anybody else? And got the right answer. Here's another one. Use the graph and the best fitting line to predict the concentration of SO2Cl2 at 1900 seconds. This would be a better exam question because it doesn't require us to actually graph the data. So from this graph of natural log of concentration versus time, I recognize that this is a first order reaction. Natural log of AT is equal to negative KT plus natural log of A at time 0. So if we want to know the concentration at 1900 seconds, what I need to do is I need to put this value in for X, which is T here, right? So this is our time. From the equation, I know that the slope is negative 0.00290. And I'm going to multiply that by 1900 seconds. And then the equation continues minus 2.30. So I'm taking the time and I'm plugging it into this equation. So then we could say, well, y equals that, right? But y is equal to the log of the concentration. So now I need my calculator. And I've got negative 0.00029 times 1900 minus 2.3 equals. And my calculator is showing me negative 2.851. At 1900 seconds, that's the value of y. Y is equal to the natural log of the concentration. So the natural log of the concentration is equal to this value. I need to undo the natural log. So the opposite of natural log is e to the x. So the concentration then is equal to e to the negative 2.851. Zero point 0.05778. Probably 2 sig figs, maybe 0.058. And the unit would be molarity because that's the unit for concentration. Any questions?
How'd you know to put that E to the...
How did I know how to do this?
Yeah.
Okay, so that's basic properties of logarithms. And there is an appendix in the book that will refresh you on that, but I'm sure there are other people that need some help with that as well. So if I have the natural log of x, then let's say the natural log of x is equal to y. Then x is equal to e to the y, because e to the natural log of x is equal to x. It's like log and anti-log in the base 10. Yeah. And we can talk more about that. We will have to become familiar with that. Logarithms really are useful things. They get a bad rap. Any other questions? Yes?
I'm just a little confused with the equation where it says y equals log.
So over here, we've got this data graphed, and so we know for this data that this is true. And I'm given a temperature, a time, 1900 seconds. So I plug that in for t, and I calculate this side. I get minus 2.851. That is equal to y. On this graph, y is equal to the natural log of the concentration. Okay? Yeah. SO2Cl2 is too many digits, so we often just use A. It's just the concentration of A.
Okay, thank you.
Anybody else? Questions? They use 3 sig figs, 5.78 times 10 minus 2. Okay, let's do another one. Cyclopropane rearranges to form propene in the gas phase. That's kind of like backstory. We can say, oh, that's nice. Now for the real stuff. The reaction is first order in cyclopropane and has a measured rate constant of 3.36 times 10 minus 5 per second at 720 Kelvin. If the initial cyclopropane concentration is 0.0445 molar, what will the cyclopropane concentration be after 235.0 minutes? This is like one of those train problems on steroids, right? Like, oh my goodness. General approach for solving word problems. When I was growing up, we called them story problems, which is friendlier, right? But general approach for word problems, read all the words and then go pick out the numbers. Write them down and identify them. So I'm going to pull out the numbers. We've got 3.36 times 10 to the minus 5. Always include units. I've got 720 Kelvin. I've got 0.0445 molar. And I've got 235 minutes. Well, we're talking about rate constants and rate laws and stuff. And it's telling us that the rate constant is 3.36 times 10 to the minus 5. So we use K for the rate constant. Now the 720 Kelvin, have we done anything with temperature? We have not. So that's just an extra piece of information. So we'll just kind of put that in parentheses. You don't always have to use all the numbers. And then 0.0445 molar, well, that's a concentration. So concentration of A, but at what time? Yeah, so this is the concentration at time 0. This is the initial concentration, right? And 235 minutes is time, so we're going to call that T. Now, someone was asking about converting? Ask it. Yes, we need to convert it to seconds. We can get a nice answer with minutes, but it's not going to be correct. So we need to convert this to seconds, 60 seconds per minute. going to write that down here. So 235 times 60, 14100 seconds. And then what are we looking for? We're looking for the final concentration or the concentration at 235 minutes at this time. So we're looking for the concentration of A at time t. Well, do we know an equation that relates these things? Yeah, we just learned it, right? The natural log of the concentration of A at time t is equal to negative kT plus the natural log, it's messy, of the concentration at time 0. So we need the rate constant, we need the time, we need A0. We've got all those things. So we'll put them into the equation. Negative, and then we're going to put in the rate constant. And the time is 14100 seconds. Now, if I didn't put the unit here of second to the -1 and I wasn't paying attention, I might accidentally use 235 minutes, but here the seconds cancel out. Plus the natural log of the initial concentration, 0.0445. And I've got just numbers on the right side of the equal sign, so I can calculate what that is. And I'm coming up with negative 3.586. If you're not sure how many significant figures to use a couple extras. And if you're not at the final answer, put in a couple extras. So I'm coming up with that. Is that the concentration? No, that's the natural log of the concentration. So what do I do to both sides to get rid of the natural log? E to the x. So I'll write it out this time. E to the x, both sides. So that gives me the concentration at T is equal to E to the negative 3.5860. And on many calculators, I've got that whole number in the memory of my calculator, and I can just press the E to the X button and then go move the cursor up and grab it and press equals, and I don't even have to type it in, and I get all the good sig figs. And there's some more digits, but the unit would be molarity. And then for significant figures, I would look for clues. I'd say, well, this other concentration had 3 sig figs, so probably reporting 3 sig figs would be good for that one. Any questions? Is that a reasonable concentration? Yeah, it is. We started at 0.0445. After 235 minutes, the concentration should be smaller, right? So if it got bigger, then you have a problem. Or if, heaven forbid, you end up with a negative concentration. That's not a good sign. Any questions? want a nice chair? You don't have to sit up here in front, but be nice and comfy. Ah, 0.0277. Okay, second order. Again, looking at this simple decomposition, here the rate is equal to the rate constant times the square of the concentration. The rate is still the change in concentration over the change in time. So we can say that these two things are equal to each other, and this again is the differential rate law. We really don't use that very much, but it's always good to at least have seen where these things come from. So we integrate that equation and we end up with this one. So this is also given in the form of a straight line. This is our y. This is b, the intercept, and that's m, the slope. The t is x. So we plot the inverse of the reactant concentration versus time, and we get a straight line. And the slope here is going to be equal to the rate constant. So consider this equation, decomposition of NO2. The concentration of NO2 is monitored at a fixed temperature as a function of time. During this decomposition reaction, the data is tabulated. Show by graphical analysis that the reaction is not first order and that it is second order. Determine the rate constant for the reaction. So we got this table of numbers. How do we show that it is not first order? No. We need to do a graph. So we graph using the first order reaction, expecting to see that it's not straight. And it says show that it is second order. So we're going to graph it again using the second order equation.
And again, we would do this on Excel.
Yes.
So we would, like if we use the first order equation, we put all those numbers in, it wouldn't be a straight line, but if we use the second order equation, it will go into a straight line.
Mm-hmm.
Okay.
Yep.
And the only way to tell that is by graphing it.
Pretty much, yeah. So if we graph that data, here's the first order graph, natural log of concentration versus time. And it kind of looks like a line, but when you actually draw the line, you see that the data goes above on both ends and below in the middle. It'd be different if it was uniformly scattered around, but it's not. It's really a curve. So it's not first order. This is the second order graph, 1 over the concentration versus time. And now we see that we do have a really nice straight line. So we were asked to find the rate constant. What's the rate constant? It's the slope. Yeah, so the equation was 1 over A at time t is equal to kt, kt plus 1 over a, 0. The zero's down here. So this is the slope. So our rate constant is equal to 0.255. And then rate constants do have units. For that, we can look at the rate law. For a second order reaction, it's the concentration squared. Rate always has units of molarity per second. And the concentration is molarity, but it's squared. So what needs to go in the box to make this an equality? I'm hearing a lot of good suggestions. I'm going to make a little space over here. Because you can kind of do this in your head, but then maybe kind of not. So let's say molarity over seconds equals x times molarity squared. And here we're thinking of the units as variables. X's and Y's, they're letters, M's and S's, right? So here I've got M squared, and there I've got M over S, and I want to get X by itself and find out what does X equal. Well, I could just like factor out an M on each side, right? Cross one off from each side. Now I've got 1 over S is equal to X times M, but I still need to get rid of that M. So we can divide by M, which is the same as multiplying by 1 over M. That just makes it a little easier to see what's going to happen over there. The M's cancel out. I get 1 over molarity times seconds is equal to X. Those are the units for a second order rate constant. They're weird, huh? 1 over molarity second? It is what it is. Any questions?
So that would be will that always be the?
For a
units
second
for a
order rate constant, the units will always be 1 over molarity second. Yep. Any other questions? So this one says, use the graph and best fitting line to predict the concentration of NO2 at 2,000 seconds. Well, 2,000 seconds, that's time, right? T equals 2,000 seconds. In our graph, on the x-axis, we're graphing time, right? So in this equation for this line, if I put the time in for x and do the math, that's going to give me y. And this is what y is. Y is 1 over NO2. Because we're graphing the y-axis and the x-axis. It's just that x and y are other things. So if I just use the equation for that line, y equals 0.255 times 2,000 plus 100. Y is equal to 610. So that means on this graph, I'm looking at a place where, y is 610 is way up here somewhere. It's off the chart. But y is equal to 1 over that concentration. So then the concentration, how do I figure that out? It's 1 over 610. Ask me questions. Do you see what I did there? Yes.
To get the 600 into the bottom, you just multiply by NO2 and divide it by 600.
So basically the question is, how did I get from here to there, right?
Just take the reciprocal.
You can upside down both sides. You can take the reciprocal of both sides. You can cross multiply and divide. You can, if we have an equation like this where we have two fractions, I can move between the top of one side and the bottom of the other side. I can move all of them to one side or all of them to the other side or switch them, and I can do the same the other direction. So I can think of, well, I move the NO2 up here and I move the 610 down there. There's several ways to think about it. It's algebra, and so you need to figure out what way works for you and then just not listen to other people. And if you have issues with algebra, please come and talk to me during lab, because I can give you a quick refresher on how to rearrange equations like this. We're going to be doing it a lot. Any other questions?
And we can set it up like we did with the first order, where we kind of just plugged everything into the original, like, second order equation.
So,
Because, like, isn't there, because it was 1 over the concentration times time.
right.
It was 1 over the initial concentration plus.
So we have the second order equation. And your question is, why don't we just plug everything into that, right?
Yes.
Because in this problem, they didn't specifically give us the rate constant and the initial concentration. We could figure out what those are from the equation, but then we're undoing what we just did when we put them back into the equation.
Does the y-intercept always represent the initial concentration?
The y-intercept here is 1 over the initial concentration, and in the first order, it's the natural log
Right.
of the initial concentration. But yeah, it typically is
Okay.
some form of that.
Right.
Yeah. Does that make sense? Yeah. Anybody else? Yes.
Why can't we just leave that at 610?
That's a good question. Why can't we just leave this as 610? Well, what we have here is true, that 610 is equal to 1 over NO2. But they asked us to find the concentration of NO2, not the reciprocal of the concentration of NO2. Yeah, excellent question. There's just a lot of pieces here, and if you're not understanding one of the pieces, the time to ask is right now. .64 times 10 to the minus 3. Okay, the zero order. The differential form ends up being this: negative change in concentration over change in time is equal to the rate constant, from putting these two ideas together. And then when we integrate that, we get this. The concentration at time t is equal to negative kT plus the initial concentration. And so we plot concentration versus time, and we get a linear plot, and the slope is equal to the negative of the rate constant. So then, of course, we're going to do some problems with this one. Actually not. I lied, yeah. Is there any questions about that one? This one is just much more straightforward because y is the concentration, x is the time, there's no reciprocals or logs or anything, it's just a nice straight line.
So it's the same as first order?
It is not the same as first order. It's very much like first order, but first order has natural logarithms. Yeah. And at the end of this section, we'll come to a table that has all of these things together. And that's one of the reasons why I give you these equations for an exam, because you've got enough going on in your head. You don't need to remember exactly which is which and which one had the negative and which one didn't. And it's just too much. The important thing is that you use it correctly. So half-life. We don't talk about half-life in Chem 1A, but in Chem 3A we talk about radioactivity and we talk about a half-life. So you've maybe have heard of half-life. Half-life is the time needed for half of the reactant to disappear, or for the concentration of the reactant to fall to 1/2 of its initial value. So if we look at an example, if the initial concentration is 0.5 and the half-life is 50 seconds, what will the concentration be after 50 seconds? We're starting out at 0.5 molar at 0, and we go to 50 seconds. That's 1 half-life, right? So this gets cut in half. The concentration is cut in half. What about after 100 seconds?
12.5.
So another half-life. From here to here, a half-life, the concentration gets cut in half. It gets cut in half and cut in half. So this would be 0.125. It does not go away in 2 half-lives. Every time it gets cut in half. This is for a first-order reaction. I'm sorry, the cutting in half business is for everything. But the half-life expression looks different for the different reaction orders. The concept is the same.
We will eventually be zero, correct?
You would eventually get to 0. But it's like all those calculus things where, the limit goes to 0. But, does it, yeah. Because you get down to undetectable amounts and you might still have, 100,000 of them. And then another half-life, and so it does take a while to get there. But eventually, yes, you would. So for first-order reaction, we can express the integrated rate law this way. Like, wait, that's not what we were looking at before. Actually, it is. So that's what we were using. This can be rearranged to look like this. So here I've got the negative KT. What I'm doing is I'm subtracting the log of 0 over here, and subtracting logs is the same as dividing numbers. And so at this point you might just want to say, yeah, okay, I believe you. In this form, though, we can calculate the half-life in terms of the rate constant. Because at T equals T1 half, we know that the concentration is half the original concentration. So we can plug that into this equation. Up at the top, instead of AT, we have 1/2 of A0 divided by A0. And that is equal to negative KT. So the A zeros cancel out. So this is equal to the natural log of 1/2. So if you put that into your calculator, the natural log of 0.5, that's equal to negative 0.693.
Is that supposed to be 1/2 A naught over A naught?
It's 1/2 A naught over A naught, yep. And so the A's cancel out. And actually the T there, I should label that T 1/2. So we've got negative K times T 1/2 is equal to negative 0.693. If we want to know what the T 1/2 is, we'll divide both sides by negative K and get that the T 1/2 is equal to 0.693 divided by the rate constant. Mm-hmm. How did I get the 0.693? That's a great question. I used my calculator and I took the natural log of 1/2. Natural log of 0.5. And that gives me 0.693 and some other digits. Any other questions?
So why did you put the 1/2 on the T?
I put the 1/2 on the T because this is the time when, this is after 1 half-life. This is, at 1 half-life, this is true, that the concentration at that time is half of the initial. It's the definition of half-life,
Okay.
T 1/2.
So if you put the half-life at the top, you have to add it to the T. Because like the initial equation, it's just the initial over the concentration at the time over the initial and then the KT. So if you just, we're switching out the concentration with time with the half-life.
So here I'm saying at 1 half-life, at T 1/2.
That is at T 1/2.
Well, this works for any time,
Oh, okay.
but we don't know what the initial concentration is.
Okay.
We know a relationship between the two concentrations. We know that now we have a concentration that's half as big as it was.
Okay.
So we can know the value of the ratio, even though we don't know the value of each concentration.
So if we were given the initial concentration, then maybe we could just use it as this and go
You
from
could,
there.
yeah.
But if it just gives us a random concentration, then
Mhm.
we have to add the half to the T.
Yeah. And this is a fairly common kind of calculation, and it does show up on exams. Like, how long would it take for 90% of the reactant to react? Well, then your ratio isn't 1/2, but the 90% gives us the information we need to put a number in there, and we don't actually need to know what the initial concentrations are. Any other questions about this T 1/2? So for first order reactions, the half-life is independent of the initial concentration. It just depends on the rate constant. So whatever you start with, after 1 half-life, you have half of it left. After 2 half-lives, now you've got 1/4. And after 3 half-lives, you've got 1/8. You just keep dividing by 2. This is what radioactive decay does. Radioactive decay is a first-order reaction. So the constant half-life only happens with the first-order reactions. So conceptual problem. So the images here depict a first-order reaction of A to B. At various times, the black circles represent reactant A, the red circles represent product B, and it's asking us what's the half-life of the reaction. So at time 0, I've just got black circles. And as time goes on, the black circles turn into red circles. How do I identify where the half-life is? Yeah, where there's equal, where half of the reactant is gone. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 dots there. So I'm going to look for a place where there's 5 of each.
90 seconds.
Looks like this one. So I have 5 black dots and 5 red dots. At 90 seconds, half of the reactant is gone. That's the half-life. Any questions?
Is this specifically for like chemicals that are like bonded together, like that form a lattice, or? 'Cause
This
in
works
solution,
for.
Wouldn't it have like a lot of surface area, and they would all?
So this works for any reaction. We can define the half-life as how long does it take for half of whatever we started with to be gone.
Yeah.
And for first order, we see that it's not dependent on the concentration, and so that would be the situation for like a radioactive decay, where it doesn't matter how much you start with, it's going to decay at the same rate. There are other reactions that would not be first order, and yet we'd still see that we still define half-life the same way, but the relationship is different. Does that answer your question?
Yeah.
Anybody else? A first order reaction, A to B again, has a half-life of 25 minutes. If the initial concentration of A is 0.3 molar, what's the concentration of B after 50 minutes? Do not use a calculator to solve this problem. Well, the half-life is 25 minutes. It's asking us about 50 minutes. How many half-lives is that?
2.
It's 2. So we take the initial concentration and cut it in half, right? That's 1 half-life. So that would give us 0.15. So we start with 0.3. We go to half of that, 0.15. So this is at 1 half-life. And we need to go to a second half-life. So we cut it in half again. Yeah, so you do it with a calculator and you end up with, or with your calculator brain, you get 0.075. Well, what's the best choice? This one's tricky. It tricked me the first time I looked at it, and it tricked me again just now. I'm like, there was a trick to this one. We started out with this much A. It's not asking how much A is left. It's asking how much B is formed. Ah.
It's A? It's B. Because if it's half-life, if half-life of A is 0.075, then that means it has to be 3 times more.
It's B, because it's 300 minus.
Yeah, so I think you're probably right. But if we take the initial concentration of A and subtract what's left after 2 half-lives, we get 0.255. So that's how much has been converted into B. It's a simple problem, and yet it's tricky, right? Everybody see what happened there? .225. So one clue there is that the answer we came up with wasn't one of the choices. What was really nasty is when they think, oh, they're going to do this wrong. We'll put that answer in there too. That's really mean. It can happen. First order reaction has a half-life of 26.4 seconds. How long does it take for the concentration of the reactant in the reaction to fall to 1/8 of its initial value? So you can do this with the equation and calculate, but you can also just divide by 2 until you get to 1/8, right? So if we start with 1 and 1 half-life, we get to 1/2, and another half-life is 1/4, and another half-life is 1/8.
So it's just 26.4 times 4?
It's 1, 2, 3 half-lives.
Oh.
So each of these arrows represents 1 half-life. So it would be 3 times 26.4 seconds. This is something about 80, I think. 79.2.
And does that only work if it's asking for the time? It doesn't necessarily, that won't work if it's asking
This
for the concentration.
this strategy will not work for all situations. It worked here because it gave us a nice fraction, 1/8. If it asked for 1/6, we couldn't do it this way, right? Yeah. Any other questions? Yes.
If it was 1/6, which equation would you use the
Well, let's do it. Let's say it's 1/6. How would we do that?
It's 2.5 times 26.4, right?
Well, maybe. So everybody's brain does math a little differently, and so you're probably like my husband, and yours goes on a different train than mine. And we can end up at the same place, but I don't necessarily know how you got there. One way to do this is to look at that equation, the natural log of a at time t over a0, is equal to negative kt. Well, actually, let's think about this. We know what t1/2 is, right? t1/2 is 26.4 seconds. So we can calculate the rate constant. The rate constant is equal to 0.693 divided by the half-life.
That's natural log.
Natural log of 1/2. So what I did is I went back to our definition of half-life for a first-order reaction. So this is given. Yes?
Should there not be a negative somewhere in there? Because if we are finding the rate constant, then shouldn't one of the variables be negative?
Well, so I'm not writing this out very clearly because I'm just making this up as I'm going over. What I'm doing here is I'm using the definition of half-life for a first-order reaction to calculate the rate constant. I'm going to take the rate constant and plug it in here
Oh, okay. So
because I can't use this equation if I don't know what the rate constant is. And I'm sure there's another way to do it, but it's not immediately obvious to me right now. So if AT is 1/6 of what it started out as, the concentration has fallen to 1/6, then we can say that AT is equal to 1/6 of A0. And now I'm pulling this equation out. The natural log of 1/6 of A0 divided by A0 is equal to, now I have my rate constant, negative 0.02625. Really poor planning here. Let's go down this way. Actually, let's just stay with K for now. How about that? That's easier. And again, we can cross out the A0s. Now we have the natural log of 1/6 is equal to negative KT. If I divide both sides by negative K, that's the time. So I need to take the natural log of 1/6 and divide it by negative 0.02625. I'm actually glad you asked. .3 seconds. Here's my K. I'm putting that in here. And doing the calculation, I come up with 68.3. Does that seem reasonable compared to what we did over here? Yeah, because it should take less time to get to 1/6 than to 1/8, right? Because 1/8 is farther. This is a good example of some skills that you're going to be needing in this course, which is the ability to take some equations and put them together in new ways. Use one equation to find this piece and then take this piece into another equation and calculate the thing that you need. So that's critical thinking. And some people are naturally good at that, but everybody can get better at it, right? So that's the goal. We're going to get better at it. Let's look at the second order. We calculate the equation for half-life in the same way. We take the second order integrated rate law, and we know that when T is T1/2, AT is equal to 1/2 of A0. So 1 over AT is going to equal 1 over half of A0 equals K times T1/2 plus 1 over A0. And then you look at that and you're like, ugh, right? We can write this out a little nicer. What if I take this 1/2 from the denominator? What does that become? Becomes 2. So 1 over 1/2 is equal to 2. And you can prove that to yourself with your calculator. Do 1 divided by 0.5. It's 2. So now I've got 2 over A0 is equal to KT1/2 plus 1 over A0. If I subtract 1 over A0 from both sides, I get 2 over A0 minus 1 over A0 is equal to KT1/2. Can I subtract those two? Yes, because the denominator is the same. So that's equal to 1 over A0. And if we want to write that so that T1/2 equals something, T1/2 is equal to 1 over the rate constant times the initial concentration. Yes?
On the exam, which form will you have that equation in?
I believe that this is given as the integrated rate law, and I believe that the T1/2 equation is also given. Here, I'm just showing how did we get that. Yeah. But you might need to use this equation to find the rate constant or to find the initial concentration, and so you'd have to rearrange. Any other questions?
So for an example, like if it gives us the time for half-life, kind of like the last equation where it's like 26.4 seconds, we can find the K with that and then plug it back into the original to find the C.
Well, here, in order to find the rate constant, you would have to know the initial concentration as well as the half-life.
Okay.
And then you could find K. And then you could plug those values. You'd have K and A0, and you could plug those in up here and find the concentration at any time you wanted, or the time for that to drop to something.
I'm assuming the 1 over A0 equals K T1/2. We can rearrange that so that it's K equals something.
Right.
Okay.
Yeah, so we can take, this is what's usually given as the equation, but you can rearrange that, and that's equal to, K is equal to 1 over T1/2 times A0. And again, it's just rearranging using algebra. So we get T1/2, 1 over K A0. So for the second order reaction, the half-life depends on the initial concentration. If we have a lower initial concentration, the half-life is going to be longer. If we have a high initial concentration, the half-life is going to be shorter. A short half-life means the reaction's going quickly. A long half-life means the reaction's going slower.
You said it again.
A short half-life means the reaction is fast. A long half-life means the reaction is slow. You kind of have to think that out every time. So if I have a long half-life, let's say it takes 100 hours to get rid of half of the reactant. If I have one that's 50 hours or 10 minutes, that reaction's going much faster. The concentration drops to half in a much shorter period of time. What about that zero order one? Well, again, we're starting with the integrated rate law and these ideas that T equals T1/2, and at that point, A equals 1/2 of A0. So 1/2 of A0 is equal to negative K T1/2 plus A0. So what I'm gonna do here is I'm gonna add, well, let's don't do that.
Could we subtract A0 and then just divide both sides by -1? Could you do that?
Yes, you certainly can. I see it in my head, but then explaining it sounds really complicated.
Just to make sure, T1/2 is 1/2 is a subscript.
Yes, it's
Okay.
1/2 is a subscript. I want to combine terms. I want to get the A0 and the 1/2 A0 together. So if I subtract, you'll see that just is ugly. Okay, we're going to have 1/2 of A0 minus This gets ugly too. There's just no way around it.
There's multiple ways to do what you're trying.
Yes, there's multiple ways, and then my brain is going all directions at the same time. So what's 1/2 minus 1? Negative 1/2. So this is negative 1/2 A0 is equal to negative K T 1/2. Multiply both sides by negative 1. Divide by K. T 1/2 equals A0 divided by 2K.
You just do 2K because that's easy to do within a fraction.
Yeah, it's just A0 over 2K is easier to look at than 1/2 A0 over K. So with these zero order reactions, the half-life also depends on the initial concentration. But here, as the initial concentration is lower, the half-life is shorter. So the half-life gets shorter as the reaction goes on. With the second order, the half-life gets longer as the reaction goes on. So there are all the things. I made this a page on Canvas so that you can pop it up and look at it anytime you want, because it's just really, really useful. We've got order, so we've got 0, first, and second. We have the rate laws for those types of reactions. We've got the units for K. We've got the integrated rate laws. We've got what gives a straight line plot and the half-life expressions. So referring to this table, you should be able to use these equations to solve problems. This one's conceptual. A decomposition reaction with a rate that is observed to slow down as the reaction proceeds has a half-life that depends on the initial concentration of the reactant. Which statement is most likely true for this reaction? So before we look at the choices, it says the half-life depends on the concentration. So that narrows it to two possibilities. It can't be first order, right? Because the first order doesn't depend on concentration. So that tells us it's 0 order or second order. The rate slows down as the reaction proceeds.
0 order.
Well, let's think about this. Let's just look at the rate law. So for a 0 order, rate is equal to the rate constant. And for a second order, rate is equal to the rate constant times the square of the concentration. As the reaction goes on, the concentration of the reactant gets smaller, right? Because the reactant is reacting and it's going away. Does the rate here depend on the concentration? No. A 0 order rate law says that the rate is constant. It doesn't matter what concentration it is. So this one will not slow down over time, but this one would. Because as time goes on, A gets smaller and smaller and smaller, so the rate gets smaller. You follow that? So those two clues tell me that this must be a second order reaction. So then we have to pick out which one of these describes a second order reaction. C. A doubling of the initial concentration results in a quadrupling of the rate. I double the concentration, 2 squared is 4. The rate increases by a factor of 4. C. Any questions? A question like this, there's a lot of little pieces in it, right? We have to be able to figure out what the order is based on the clues. And we also have to recognize which of these things describes that order.